Welcome, everybody. We're going to talk a little bit about our lesson on series number 5. It's going to be alternating series. So, what is meant by an alternating series? Well, there's two of them I can think of right off the top of my head. If you recall our Maclaurin series or Maclaurin polynomial for sine x, remember it was all the odd powers, x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, dot, dot, dot. That's an alternating series. Why? It goes from positive to negative to positive to negative. That's what's meant by alternating. Likewise, our cosine Maclaurin polynomial, which started with 1 and then did all of the even exponents and factorials like this. That is another alternating series. So other than those two, you might say, well, how can I tell if something alternates that's not like the Maclaurin for sine and cosine? And in short, this is how. Whenever I see a series that says something like n equals, again, I could go from n equals 1 to infinity. I could go from 18 to infinity, 180 to infinity. There's no real, I guess, criteria about my starting value. I'm just going to use the ones that are here. But I have a negative 1 to the power n. That's what tells me it alternates right there. The negative 1 to the power n. And then, yeah, typically it's times some a sub n. You say, well, what's a sub n? Well, a sub n could be like n squared. It could be like 2n minus 7. It could be basically any expression. So an alternating series, basically, it consists of two parts. You have your alternating part. That's the negative 1 to the here. And this is whatever else it may happen to have in it. And that can vary. So why does this alternate? Okay, well, I'm going to ignore the an like whatever the other thing is, but here's why it alternates. If I start at 1, I take my first term would be negative 1 to the power 1. Now I'm working my way up to infinity, so my next term would be negative 1 squared, and then negative 1 cubed, and negative 1 to the 4th, and so on and so forth. When I take a negative and raise it to odd powers like 1 and 3, that's going to make it negative. Raising it to an even power like 2 is positive. That makes it alternate. You might say, okay, I get that, but what about this one, the n plus 1? How does that still alternate? Okay, same deal. Again, I'm going to start at 1, but really there's nothing magical about it. You could start at 7. It doesn't really matter. So let's go negative 1 to the n plus 1. So my first term would be negative 1 to the 1 plus 1. My next term, working my way to infinity, would be negative 1 to the 2 plus 1, and then negative 1 to the 3 plus 1. And basically what happens is I get this, dot, dot, dot here. So I get negative 1 squared, which is positive 1, plus negative 1 cubed, which is negative 1, and then negative 1 to the 4th, which is going to be positive again, dot, dot, dot. So really all it does is by putting the n plus 1 on it like this, all it does is it starts it here and blows off that first term, that first negative 1. So both of those little formulas there, when you see a negative 1 to the n or the n plus 1 or n plus 3 or n minus 7, whatever like that, n minus 2, those are all going to give you alternating terms. So how does it work? Well, here's the first thing. Alternating series test does one thing. It tells you if something will converge only. It does not tell you that something diverges. You might say, well, if it doesn't converge, then it obviously diverges. No, it's either you are 100% sure that it converges, it does that, if it works properly, or it's like, I can't tell. I'm not sure. So you cannot determine divergence from it. But luckily, this is kind of a cool thing here. That you might remember us talking about our nth term test, how it only determines if something diverges. It cannot determine convergence. So typically, when nth term fails and it's inconclusive, try alternating series. It might pick up where the other one fails. Or likewise here. For the alternating series, it requires your limit at infinity equals 0. You say, well, what if it doesn't? Then I can't say it converges by the alternating series test. You're right. But if the limit is not equal to 0, then I know it 100% diverges, not by the alternating series test, but by the nth term test. So the two kind of feed off each other is what it amounts to. Where one might be inconclusive, the other test might be used to kind of pick up where the other leaves off. So what are the criteria? Well, first off, you want to ask yourself this question. Does the series alternate? If the answer to that is yes, then you go and check out number 1. It says a sub n plus 1 less than an. What does that really mean? Well, what it really means is that my new term, like whatever the next term is, like if I've got like 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever terms here. So like here's my a1 plus a2, a3, a4. So this is like my old term or my previous term. A5 would be my next term or my new term. So does the new or the next term, is it less than the previous term? So like if this is less than that, okay, it's decreasing. And then if this would be less than A6, see, if all of these keep being less than the one prior to it, that means I'm sorry, I had this backwards. If your new term or your next term is less than the one before it, so like here, if you're going from bigger to smaller, well, that means you're decreasing. That's all that's saying. So that you never increase. Your terms never increase. You might say, well, they go positive, negative, positive, negative. That's eventually it's going to increase. No. We're talking about the absolute value of it. We're talking about just, again, if you look at the thing here, when I compare does it decrease? I'm ignoring the alternating part. I'm going to take the plus minus out of it. I'm looking strictly at like the magnitude of it. Again, I hate to bring in physics here, except I love physics and I'm going to. Remember vectors, speed, magnitude, and direction. So I ignore the direction and look at just the magnitude of the term, the size of the term, how big it is without the negative or the positive direction. And then lastly, so if it's decreasing or never increasing in absolute value, and if the limit equals 0 as n approaches infinity. So if it satisfies this and these two, then it converges. And geometric series tests, we've kind of done that to death. I'm not going to go over that more. And then here's the official write-up for what alternating series looks like. So let's practice a little. I have 8 different series. Some of these alternating series tests will work beautifully. Sometimes it will fail. And then we'll see where we go from there. So first thing I look here. Again, let's look at our criteria again. Number 1, does it alternate? If so, proceed to number 1 and number 2. That's where you look for AN to be decreasing or the ignoring the alternating part. Whatever else is there, is it getting smaller or not getting bigger? And then lastly, does my limit as n approaches infinity equal 0? So let's look here. Alternating, yeah, I got -1 to the n. Check on the alternating part. Decreasing, okay? Here's what I mean when the last page when I talk about n equals 1 to infinity, and I'd say like -1 to the n times an. So I'm going to basically take out, again, I'm going to write my -1 to infinity. I'm going to take out the -1 to the n. I'm going to take out the part that makes it alternate. and I'm going to look at what's left. Well, what would be left would be like a imaginary 1 on the top and then times n. If I were to multiply these two together, it would make -1 to the n over n. So when I examine the does it decrease kind of deal, I'm only looking at this part. Now, I don't need you, again, to do like some fancy test, where you got to find f prime and make it 0, and then it's decreasing. No, I don't need to go that hardcore on this. It's more of an intuitive kind of thing. So I'm just going to throw in a couple of terms and ignore the alternating nature of it. So like I start at 1, so like my first term would be 1 over 1. And then I'm going to infinity, so it'd be 1 plus 1, and then 1 over 2, and then 1 over 3, and 1 over 4. And yeah, as these bottoms keep getting bigger and bigger, like as it goes to infinity, yeah, I can see that it's decreasing. Bigger bottom means smaller fraction. And then lastly, I'm going to find the limit as n approaches infinity of the an, which is 1 over n, which would be 1 over infinity, which basically approaches 0, so check on all three fronts. So if it satisfies all three criteria, I can say this. Since the series, if you want to write the whole series out, have a blast, is alternating, and that a sub n is decreasing, and the limit as n approaches infinity of a sub n equals 0. Since all three of these criteria are met, then the series converges by the alternating series test. And yes, you may write AST. The graders will know exactly what it is. Otherwise, they shouldn't be doing Cal 2. These guys are teachers, college professors who have taught Cal 2, the graders, so they know exactly what this is. And so that's what a proof and an example looks like, and a justification looks like. So let's look at this next one. Does it alternate? Sure. Before I look at the decreasing part, I see kind of a red flag here right now. Let me show you. If I do the limit in infinity of the an of the n over 2n minus 1, again, the minus 1's insignificant. That's going to give me n over 2n. Which simply gives me 1/2. You say, oh no, it doesn't equal 0. Alternating series test doesn't work. I agree. I cannot use the alternating series test here, but the nth-term test picks up where the other left off. So if the limit in infinity was 0, I would continue using the alternating series test. Since it's not 0, I can say, since the limit as n approaches infinity of a sub n does not equal 0, the series diverges by the nth term test. So just because it alternates doesn't mean I have to use the alternating series test. If it's going to be inconclusive because that limit doesn't equal 0, well, does not equal 0, excuse me. That's where the nth term test picks up. If this fails, here's your other option. Okay, this one, does it alternate? Sure does. Again, does it decrease? Maybe that's not quite as easy to see, or maybe you don't want to write down all the terms. Let's do this. Let's take that limit as n approaches 0, or infinity again. If this checks out, then I'll try the whole decrease and try a few terms and see if it makes sense. So I'm going to rewrite the end of the square root of n as n to the half. And then n squared plus 1. Again, the plus 1's insignificant. And I've been told that when the top, or like when you're dividing, you want to subtract. So I get limit n approaches infinity. Half minus 2 is to the negative 3 halves, which basically gives me 1 over n to the 3 halves. And if I plug in, if I plug in infinity, that's going to give me 1 over really huge. That's 0. So, does it alternate? Check. Does the limit equal 0 at infinity? Yes. So now let's check for decreasing. And honestly, anytime it's bottom heavy, where the highest power on the bottom is bigger than the highest power on the top, it's going to decrease, but you can find a couple of terms. Let's just plug in the 1. So my first term would be square root of 1 over 1 squared plus 1, which would give me 1 over 2. Again, I'm ignoring the alternating part. Then if I plug in 2, my next term would be root 2 over 2 squared plus 1, which is 5. And let me do one more here. Or you might say, well, let's try like something like 100. Okay, let's do that. So we got dot, dot, dots, and then we go up to like 100. Square root of 100 over 100 squared plus 1. So that would be a 10, and that would be a 101. So what do I see? The top is getting bigger. I can see that it's actually getting bigger here. 1 to square root of 2, yeah, that's bigger. That's like 1.41, like that and change. So the top got a little bigger. The bottom went up by like 3. So the bottom got bigger by more than the top did. That tells me it's decreasing. So it does satisfy all 3 criteria. Now again, that last little step here where I showed you like finding the terms to show this decreasing, typically I don't do that because I can tell, if it's bottom heavy, if the power on the bottom is bigger than the power on top, it's going to decrease. So since the series is alternating, okay, A sub n is decreasing, and the limit as n approaches infinity of an equals 0, the series converges by alternating series test. Okay. Part D, does it alternate? Check. Is it bottom heavy? No, it's not bottom heavy. So that tells me it's probably not decreasing. So what do? I do my limit at infinity again. The nth term test is probably my main go-to unless I like recognize it as a Taylor series or like a geometric. It's pretty much my go-to because I can figure out pretty much in my head what's going on here. So that's n to the 5th over n to the 5th plus 3. The 3 is insignificant. Again, this is something I'm doing in my head. N to the 5th over n to the 5th is 1, which more importantly is not 0. So all this stuff that I'm showing you right here, I can figure that out in my head, and so can you, I would imagine. Maybe not right now, but in time for some of you. But what happens if the limit at infinity is not 0? Forget all about the alternating series test. I could care less. I would say since the limit as n approaches infinity of an does not equal 0, the series diverges by nth term test. Again, that's something, my hope is that you get to the point where you can just look at it and say, hey, wait a minute, the limit at infinity is not going to be 0. It's not bottom heavy. And then you can go straight to this. Okay, I'm going to skip here for a second. I'm going to go straight to F. Why? Because I can see right now this is to the highest power 1. That's to the highest power 1. I know if I take the limit as n approaches infinity of 6n plus 5 over 7n minus 8. The 5 and the 8 are insignificant. 6n over 7n gives me 6 over 7. More importantly, not 0, so my write-up for number 7, for letter F, exactly the same as what I did here. So I will write it out right, because if you don't do it when you turn in your notes to me, I'm going to butcher you on it, so I guess I'm not going to be a hypocrite here. Or I'm going to avoid being hypocritical. Since the limit n approaches infinity, an not 0, then the series diverges by the nth term test. So that's why I say, and even here, this one doesn't even alternate. I can't use the alternating series test, but honestly, nth term test is the first thing I look for, because it's evaluating limits in infinity is pretty easy to do. So then what about E? Well, E doesn't alternate. I don't see like that negative 1 to the whatever power here. So how do I deal with, oh, wait a minute. I remember we talked about this when we had like something to the n, something to the n. This one's geometric. And whatever it is that's raised to the n power, in this case, the 3 and the 5 is your common ratio. So I would say that since the absolute value of the ratio, which ends up being 3/5, since that's less than 1, and that's really an ugly way to write less than 1, the series converges. And I'm going to leave that blank for a second to whatever by the geometric series test. But what am I doing here? Okay, maybe I'm freaking out, but no. What I'm doing is that when you get a geometric series that converges, not only can I say it converges, I can tell you to what it converges. You might recall us saying that, like, the sum of the n terms is a over 1 minus r. A is your initial term. R is your ratio. And I know my ratio is 3/5. All that remains is I've got to find my initial term. How do I find my initial term? I take the initial value 1 right there, and I plug it in for n. So 3/5 to the 1 is actually 3/5. So that's my initial. Now I do a little algebra. That's 3/5 over, again, the 1 I can rewrite as 5/5. So 5/5 minus 3/5 is 2/5, which gives me 3/5 times, copy, change, flip, converges to 3/2. So if you get a geometric series that converges, you can actually say to what it converges by your geometric series test. Okay, 2 more to go. Does this alternate? Yes. Is it also like raised to like an n or n plus 1 power? So although this is alternating, I'm going to treat it as a geometric series. And what's my ratio? What's being raised to the n, or the n plus 1 or the n plus 2? Well, the negative 2 is, and then so is the 7 on the bottom. So this write-up is going to look eerily similar to this one. I would say since the absolute value of my ratio, which in this case would end up being not negative 2/7, but 2/7, because you ignore the absolute value when you compare it to 1, then the series converges to, and I'm not sure what it converges to. We'll figure that out, but it's by GST, geometric series test. So let's find what it does converge to, shall we? Again, it's a over 1 minus r. My r is going to be negative 2/7. My a, my initial term, I'm going to plug 0 in for n in each case. So my a will be negative 2 to the 0 plus 1 over 7 to the 0. 0 plus 1 is 1. Negative 2 to the 1 is negative 2. 7 to the 0 is 1. My initial term is negative 2. So I get negative 2 over. Negative is positive. And 1 is 7/7, so that's 9/7. And then multiply by the reciprocal, so negative 2 times 7 over 9. It converges to negative 14 over 9. Just like that. Okay. Next one, I can kind of tell just by looking at it what's going down here. Do you see how the bottom has factorials on it? And you might remember me telling you that, that factorial has the highest relative growth rate. It gets bigger faster than other functions. So bigger faster than squaring, raising to the 4th, raising to the 6th, all that kind of fun stuff like that. I know this thing is extremely bottom heavy. You say, so? Well, look, it goes from positive to negative to positive to negative. So does it alternate? Why, yes, it does. Is it decreasing? Well, pi over 6, you say, the power is getting bigger, so it's going to be getting bigger on top. No, it's not. Because, like, if I take, like, 1/3 and raise it to the squared power, it becomes 1/9. So when you have a fraction less than 1, raising it to a power does not make it bigger. However, look at this bottom. 2 factorial, 4 factorial, 6 factorial. That bottom gets a lot bigger. So it's alternating, it's decreasing. And if I were to take the limit as n approaches infinity, eventually I'd have like something over infinity factorial. I could give a rip what's on top. That approaches 0. So this one I would write up as something like this. Since the series alternates, a sub n is decreasing, and the limit as n approaches infinity of an equals 0, then the series converges by alternating series test. And there you have it. There's your kind of brief intro into alternating series test. We'll talk more about it in the next lesson when we talk about series error as well. Hope this helps. Bye, guys.